In this class, we have to discuss one of the important concept, that is generation of frequency modulated signals. So to generate the frequency modulated signals, we are having two methods. So there are essentially two basic methods of generating frequency modulated signals. So in that, first one is the direct to FM. So that is also called as a parameter variation method. So second one is indirect FM, that is represented as Armstrong-Sun. So these are the two methods. By using these two methods, we have to generate the frequency modulated signals. So in that, the first method is direct FM. So in the direct method, the carrier frequency is directly varied in accordance with the input baseband signal. So in the direct FM means, so the carrier signal having, that means the carrier signal having some frequency, that is called carrier frequency. That carrier frequency is directly variation, that means this directly changes by using the input, whatever we are giving the input signal, that is the baseband signal. So by according to that baseband signal, so the carrier frequency is directly changes. So which is readily accomplished using a voltage controlled oscillator. So in this process, the carrier frequency is varied by using this voltage controlled oscillator circuit. And in the indirect method, so the modulating signal is first used to produce a narrowband FM signal, and frequency multiplication is next used to increase the frequency deviation to the desired level. So in the indirect method, so first the whatever we are giving the signal, that is the modulating signal, that modulating signal is first converted into the narrowband frequency modulated signal. So the modulating signal first used to produce a narrowband FM signal, then after the frequency multiplication is next. So the next process is the frequency multiplication, then after to increase that frequency deviation, so up to the level, that is the desired level. So these are the two methods. So we are using these two methods to produce or to generate the frequency modulated waves. So what are the different methods of FM generation? So we are using basically we are using two methods, so direct FM and indirect FM. So within that, so what are the stages are occurred to generate these FM signals? So in direct methods, so that is the first one is direct, that means we are using the varactor diode modulator. So to generate this FM modulator in direct method, so one is varactor diode modulator, and the second one is by using the reactance modulator. So we can generate the FM so by using the reactance modulator. And next one is the frequency stabilized reactance FM transmitter. So using this circuit also we are generating the FM signal. And next one is a cross by direct FM transmitter, and next one is a PLL direct to FM modulator. So PLL nothing but the phased lock loop. So by using that PLL direct FM modulator, so we are also generating the FM signal. And next one is indirect method, that is Armstrong indirect FM transmitter. So these are the two methods. So we are using different circuits to generate the FM signals. So in that, the first one, the first direct FM method is the parameter variation method. So here the first FM generating method is direct FM. So in that direct FM we are using the parameter variation method. So by using that, so to generate the fm wave in direct method, so the fm generated by vco, that is voltage controlled oscillator. So here is so to observe that block diagram, so that is a voltage variable capacitor and one of the input signal modulating signal m of t, and the inductor, so that is to reminder of the oscillator circuit. So VCO, that means the voltage control oscillator, is basically a sinusoidal oscillator. So with this having a capacitive or reactive elements. So the voltage control oscillator is basically a sinusoidal oscillator, and that sinusoidal oscillator having a capacitive or reactive element. So in voltage controlled oscillator, the frequency of an oscillator is directly controlled by the message signal m of t. So in this parameter variation method, the carrier frequency, so the carrier frequency of an oscillator is directly controlled by using that modulating signal m of t, that means voltage signal. So here we are assuming that voltage signal, because the message signal is typically measured in volts. The message signal is typically measured in volts. So here the figure shows that fm generation which uses a Hartley oscillator. So here is we are using the center type capacitance, that is CV and C0. So inductors, we can determine the frequency of oscillator. Here we are using the capacitor, that is we are arranged in center type capacitance, and we are using the inductors. So by using this we can determine the frequency of oscillator. So here is the frequency of nothing but, so f is equals to 1 by 2 pi root LC, or 2 pi root LC whole power minus 1. So that is the principal difficulty here is to maintain a stable carrier frequency over extended period of time. So this is about the generation of direct FM by using the parameter variation method. And one more method is a varactor diode modulator. So that is observe this figure. So here is the oscillator tank circuit and varactor. So here we are using the varactor diode, and so the resultant signal is audio frequency output. So that is varactor diode modulator. And one more important method is basic reactance modulator. So by using this basic reactance modulator, we are having to generate the FM modulator. So here is we are observe that figure. So here we are using the FET transistor, that is gate. So the FET transistor having the three terminals, that is gate, drain and sources. So here we are using one more that is capacitors and resistors, and the current I and the impedance Z. So here is the FET reactance modulator behaves as a three terminal reactance. So here the FET transistor are acting as a three terminal devices, three terminal reactance. So basically the FET transistors having three terminals, and like this, so the FET reactance modulator act as a three terminal reactance, so that may connected across the tank circuit of the oscillator to be frequency modulated. That FET reactance modulator is connected across the tank circuit of the oscillator to be frequency modulated. So here the value of the reactance is proportional to the transconductance of the device. So here the FET reactance is directly proportional to the transconductance of the device. So what is the transconductance, as already known that. So that is which can be made to depend on the gate bias and its variations. So this is occurred by using the gate bias. So like this, gate bias and its variations. And what are the important points from that varactor diode, from that reactance modulator. So we are assuming some important. So what is that? So here is the following should be noted from C equivalent is equals to transconductance Gm into Rc. So like this, transconductance Gm into Rc. So the first one is this equivalent capacitance depends on the transconductance and can be therefore varied with the bias voltage. And the second one is the capacitance can be originally adjusted to any value by varying the components R and C. So the capacitance is originally adjusted to the value by using the components R and C. It means resistor and capacitor. So in practice, the gate to drain impedance is 5 to 10 times the gate to source impedance. So within this method, so the gate to drain impedance is 5 to 10 times more to the gate to source impedance. So here is, let us assume Xc is equals to NR. So that means Xc is equals to 1 by omega C, that is equals to, we are represented as N into R. Then by rearranging that equation, so C is equals to 1 by omega into NR, so that is equals to 1 by 2 pi FNR. So omega nothing but 2 pi F. So then C equivalent is equals to Gm into Rc. So Gm into R, so the value of C, so we know that, so what is that, 1 by 2 pi FNR. So that is substituted in this, then the resultant equation is C equivalent is equals to Gm by 2 pi Fn. So like this, so the basic reactance modulator, so the impedance Z, seen that at the input terminals A to A is almost entirely reactive. The input terminals, so like this, so A to A almost the impedance Z is almost entirely reactive, that is the value of Z is equals to minus J Xc by Gm into R. So this impedance is quite clearly a capacitive reactance. So this impedance shows that, so it is clearly a capacitive reactance, which may be written like this: X equivalent is equals to Xc by GMR. So that is equals to 1 by 2 pi f Gm into Rc, that is equals to 1 by 2 pi Fc equivalent. So from the above equation, it is seen that under such conditions, the input impedance of the device is a pure reactance, and it is given by C equivalent is equals to transconductance Gm into Rc. So so what are the parameters comparisons? So we are shown in the table format. So observe this table format. So the name is RC capacitive, RC inductive, RL inductive, and RL capacitive. Then what are the impedances, gate to drain and gate to sources. So conditions, what are the conditions, then what are the reactance formulas. So this is about the generation of FM by using the reactance modulator. And one more method is the transistor reactance modulator. So in direct FM, so one more we are using the transistor reactance modulator. So observe this figure. So here we are using the reactance modulator and the oscillators. So this is represented as transistor reactance modulator, like this. So these are the methods using direct FM, so we can generate the frequency modulated signals. So this is the direct FM technique. And next method, that is second method, is indirect FM. So here we are seeing some the block diagram. So how to generate that FM signal. So the block diagram have consists of the integrator, narrowband phase modulator, and crystal control oscillator, as well as the frequency multiplier. So in this, to observe this block diagram, so we are applying the input signal, that is the baseband signal m of t, to the integrator, and the output of that integrator will gives to the narrowband phase modulator. So the output of this narrowband phase modulator represented as S1 of t. So like S1 of t, and that S1 of t will gives to the frequency multiplier. Then the frequency multiplier produce the resultant signal, that is FM signal S of t. So here the block diagram of the indirect method generating a wideband FM signal. So to observe this figure, so here the narrowband phase modulator output we will assume S1 of t. So let S1 of t denote the output of the phase modulator. So what is the phase modulator output? So already known that. So what is the standard form of phase modulator? So that is S1 of t is equals to A1 cos 2 pi f1 t plus 2 pi kf integral 0 to t m of t dt. So this we will assume equation 1. So once again I will repeat. Here S1 of t represents the output of the narrowband phase modulator. So already we know that the output, what is the standard form or what is the output of phase modulator. So here S1 of t is equals to A1 cos 2 pi f1 t plus 2 pi kf integral 0 to t m of t dt. So this is the resultant phase modulator output. So this equation we will assume as 1, first equation. So in this equation f1 represents the frequency of the crystal control oscillator. F1 represents the frequency of crystal controlled oscillator, and kf nothing but it is a constant value. Kf represents it is a constant value. So for a sinusoidal modulating wave, that is the baseband signal m of t, the output of this S1 of t. So what is the m of t? We can represent m of t is equals to am cos 2 pi fmt. So this m of t value we can substitute the phase modulator output, that is S1 of t signal. So that is the resultant signal of this S1 of t is, so A1 cos 2 pi f1 t plus 2 pi kf integral 0 to t. So m of t nothing but am cos 2 pi fmt dt. So once again I will repeat. So m of t value అనేది మనం S1 of t అంటే phase modulator output లో సబ్స్టిట్యూట్ చేస్తున్నాం. So what is the S1 of t value? S1 of t is equals to A1 cos 2 pi f1 t plus 2 pi kf integral 0 to t am cos 2 pi fmt dt. So rearranging that equation, so we can assume the final we will get the final FM signal is S1 of t is equals to A1 cos 2 pi f1 t plus beta 1 sin 2 pi fmt. Here beta 1 represents the modulation index. And next the phase modulator output is next multiplied by n times. The phase modulator output is next multiplied by n times. So it is multiplied by n times the frequency by the frequency multiplier, producing the desired wideband FM wave. So the resultant is S1 of t is equals to A1 cos 2 pi n f1 t plus 2 pi n kf integral 0 to t m of t dt. Then rearranging that equation, so that is S1 of t is equals to A1 cos 2 pi fct plus 2 pi n kf integral 0 to t m of t dt. So in the case of sinusoidal modulating signal, the S1 of t becomes, so that is the S of t is equals to AC cos 2 pi fct plus n into beta 1 sin 2 pi fmt. So here is it can produce the resultant signal, that is WB FM signal. So S of t is equals to AC cos 2 pi fct plus beta sin 2 pi fmt. So this is the desired signal. This is we wanted that signal. So here is beta nothing but the modulation index for WBFM. So that's why by choosing and properly we may set the final value of the modulation index beta of WBFM signal at any desired value. So this is about about the indirect FM method. So by using this block diagram we will generating a WBFM signal. So here is one more block diagram, that is the block diagram of frequency multiplier. So here in the inbuilt of this frequency modulator, so which process are done. So here is a memoryless nonlinear device and band pass filter with band frequency n into fc, and the input of this one is the FM signal S of t with carrier frequency fc and modulation index beta. So this is the generation of FM signal by using the indirect method, and the complete session is generation of FM signals by using two methods. So one is direct FM and second one is indirect FM. So in indirect FM, so different circuits or different concepts are available to generate these FM signals. So this is the generation of FM signals. Thank you.